votre conférence Télécom Paris.
My name is Laurent Bienvenu and I'm a professor emeritus at the University in Bordeaux.
My name is Habilitation and I am professor at the University of France.
Marzeton, I'm a professor here at Bordeaux University, computer science.
So Vasco in online, I don't know if you can.
And Vasco, if you can introduce yourself, people can hear you.
Okay, so my name is Vasco Bradka. Hello from Munich. I'm professor at the University of the Armed Forces in Munich.
Okay, so thank you. So it's now your turn to talk about your work.
Thank you very much. So, thank you all for being here. So I'm going to give an overview of my research. So obviously it's always difficult to make choices, so the manuscript that I wrote is already a subset of what I do, what I've been doing for the last 15 years. And the talk is also a subset of that, so I hope I will still manage to make it interesting enough for you. So I've used this grandiloquent title. It's a tale of computability and probability. And the style, maybe for people who recognize it, it's a tribute to my Normandy roots and the Bayeux tapestry. So let's get started, if possible. Oops.
Don't fresh with computer scientist.
No, never. Sorry, my slides are blocked. No.
Just click on the slide, maybe just click
The
with the mouse.
slides stopped working. Yeah. Now I think it is good. Okay, sorry about that. So, just going to say a very few quick words. I think most people here will know the setting of computability theory, but I felt I should recall just a few basic notions. So, the setting of my research is computability theory. So basically, I'm interested in questions like, what does it mean for a problem, for a function, for an object to be computable? What are natural examples of such like non-computable functions, non-computable objects? Among those that are not computable, are there things that are harder to compute than others? If you assume you can compute one, how can you compute the other? And I want to stress that they will maybe be apparent all through the talk is I'm not a complexity theorist, so I never care about computation time. Like for me, it's like, is this computable? Is this not computable? I typically do not care. There will be maybe a small exception you will see in one of the sections, but more or less we don't care about computation time. So, the definition of a computable object probably is well known. So it's you say that something is computable basically if some program, some Turing machine, some RAM machine, your favorite mode of computation can realize it. So let's imagine we work with the binary alphabet 0, 1. I'm going to set I'm going to present briefly Turing machine. So a Turing machine is a machine which has an input. The input can be a finite or infinite, and more importantly for this talk, the output can also be finite or infinite. Okay, so it looks like this. So what's a Turing machine? So you have your input here. So again, here it's infinite, but it could also be finite. And you have a head. So this head is like a finite machine. So it has only finitely many states, and it reads some bits here, and it can also, it has a work tape, so it's like a, brouillon, right? It's a scratch paper. And then it has an output tape. This one is read only, this one is write only, and here it can just do whatever it wants, right? So it will have like a sequence of steps. And there you go. And this, if I have a function which is realized by a Turing machine, then I say that this function is computable. So a notion that also will come up in my talk is Kolmogorov complexity. Again, for people who've heard me give talks at LABRI, I'm almost positive that Kolmogorov complexity came up at some point. So what is Kolmogorov complexity? If I give you a finite binary string, I define its Kolmogorov complexity as the length of its best description by a computer program. So we have an x, and I define k of x. It's the length of the shortest program for a universal Turing machine. That is a Turing machine which can simulate all others. There exists such a machine, which produces x. So again, you really have to think of what is the shortest program that describes my x. And so basically, if you have a given x, the Kolmogorov complexity is somewhere between 0 and x. So 0 is like a very simple x. Imagine if you have like a billion zeros, or you have a very short program that prints your x. Right? It's like for I equal 1 to 1 billion, print 0. Extremely short program for a very long string. So that at such an x will have Kolmogorov complexity very close to 0. On the other hand, if you pick an x completely at random, like a completely random sequence of a billion bits, more or less the best program you will have to describe it will be print, and you're going to have to give it explicitly. So we will be in this end of the spectrum. Okay, so this is really how you have to think about Kolmogorov complexity. Low complexity is very simple, high complexity is complex or random. So we will come back to this. It's an interesting thing that these two are equated. It's not always, depending on which scientific theory you're looking at, the word complexity and randomness can have different meanings. For the sake of Kolmogorov complexity, for me, like for Kolmogorov complexity, something complex is something random. And this is good for finite objects, but we also have ways to define randomness for infinite objects. So that also will come up a bit in the talk. So algorithmic randomness basically is how do we define randomness for an infinite binary sequence. So there are many, many ways to do this. It's an entire theory. There's an entire zoo of possible definitions. The main one, the one that is the most successful, really at capturing everything, is the so-called Martinov randomness. So I say that an infinite sequence is Martinov random if basically its Kolmogorov complexity of the first n bits is always greater than n up to some fixed constant. So you will notice here I use kp and not k. It's because I need this very slight variation of Kolmogorov complexity. So you can just not worry about it. You can just basically think of an infinite binary sequence as being random if all its initial segments are maximally complex. But if you really want to be precise, you cannot use the regular Kolmogorov complexity. You need a slight variant of it, which is almost equal to k. So it doesn't make a huge difference, but with k it doesn't quite work. It's in fact not the actual definition that Martinov gave, but it's an equivalent definition. Okay, so that's basically the settlement. And I guess the guiding question of this entire manuscript that I wrote is basically this question: can randomness add computability? So this particular question is not mine. It's actually something that I saw on Math Overflow several years ago. And it was not the only question of this type that was being asked, but I thought it was a kind of a catchy title. So I'm not going to read the entire thing. It's basically this user was asking, is it possible to, we know what's computable, what's not computable, but is it possible to use randomness to get something which is essentially deterministic, like a function, but not recursive? So I'm not sure exactly what he meant by essentially deterministic, but like basically, okay, so I have this object, and I know I cannot compute it, say, by a Turing machine, but can I use randomness to get access to that object? And it's a very natural question, and I have to say it's true that when you typically, if you ever get a chance to learn about computability theory, usually you learn it at the same time as complexity theory. In complexity theory, they will tell you about classes such as BPP, etc., where you have like probabilistic algorithms, but they never talk about this in the setting of computability theory, right? So let me just ask a question. You learn normally, the very first time you hear about computability theory, very quickly, you learn about the halting problem, right? So the halting problem, it's like given a program, does it hold or not? And you can think of that problem as an infinite binary sequence. When I list all the possible programs, I put a 0 if it doesn't hold, I put a 1 if it holds. Right? So this is a non-computable sequence because the halting problem is not decided. Given the program, there is no algorithm which tells you whether this program will hold or not. But maybe, with a probabilistic algorithm, you could do that. It's possible, right? That maybe you do some random trials and you kind of test your programs, and then it's like, looks like it's going to hold. Okay, I'm going to go on a whim and just say it holds, right? So this would actually be nice. Right? Say, okay, it's undecidable, but we can almost surely generate it. So, is there any hope? Well, before I can answer this question, I need to tell you what, to make my question precise, here I mentioned a probabilistic Turing machine. So, what is a probabilistic Turing machine? Well, you have two answers. The first one is like, usually it's how it's defined in complexity theory. So you have a Turing machine, and the decision that it takes at every step is probabilistic. That is, it's reading something, it's reading a square, like a symbol, it's in a state, and it's decide where it's going to go next in a probabilistic fashion. Right? So the machine itself has internal randomness. But for me, it's more comfortable to think about my machine being deterministic, and just the randomness is external. On some tape, somebody has given me a completely random sequence, and I'm going to use these random bits to take my decision, right? This is what happens when you want to run a very heavy random simulation. You just have like a DVD or USB stick with all the random bits already given in advance, right? So and this is much better for computability theories, and also then I can ask questions about this random tape of Oracle. I can ask what level of randomness is on it. Right? Because I have a way to gauge randomness for infinite sequences, so I can also talk about the level of randomness for that random tape. So it would look like this. This is my Turing machine, and I add this random tape here, right? And this, my machine, is going to have the input, the randomness here, and it's going to do the same thing. It's going to have this work tape, and it's going to have its output. Okay, so back to my question now. Either a probabilistic Turing machine, which has an infinite potential output, that's going to print 0 prime, which is called the halting set, with probability, say, 99%. So, as you can imagine, no, that would be way too good to be true. Actually, for the halting set, it's pretty easy to prove because you can use Kleene fixed point theorem. Right? Kleene fixed point theorem allows you to consider a program that knows itself. So suppose I'm a program and I know myself, I know my own code. Well, I'm waiting for this probabilistic algorithm to tell me what it thinks about me. I can try the algorithm many times. And if I see that with probability, say 98%, it says that I do not hold, then I'm going to hold. And if I see the opposite, I'm going to do the opposite. Right? So basically, I defeat the probabilistic algorithm. Right? So basically, that means the algorithm must fail. But in fact, this trick is nice for the halting problem. It is just a much more general result. In fact, it's completely impossible to use randomness to add computability in the following sense. It's a very old theorem, actually. People realize that very early on. That if you have a probabilistic Turing machine, such that it produces a given infinite sequence, where x is a fixed infinite sequence, such that you have a positive probability with your probabilistic Turing machine to print exactly this x. Right? Which I think is more or less what the user was asking in math overflow. Well, then this x is in fact a computable sequence. So you have de-randomized your randomized algorithm in the setting of computability. Okay, so basically what does that mean? That means randomness is useless. There's no point using randomness in computability theory, so the talk is over. Right? The crystal, and well, obviously not quite yet, because there is another interesting setting, which I guess is other questions of math overflow were on this type. Is now instead I don't give you a single sequence x, I give you like a kind of a task, the problem of generating something that a deterministic Turing machine cannot do. Right? So I have a class of objects that are of interest to me, and I say, can I get one of these objects, some of them, using probabilistic means? And there the situation, of course, changes dramatically. Why? Because we have a very stupid example. If my goal, my hope, was to produce a non-computable sequence, well, I'm just going to use my random bits, and I'm going to print them verbatim. I don't change anything. I just get my my random sequence, and I print that random sequence. Well, with probability 1, it's going to be non-computable. There are only countably many computable sequences, so if I just print my random bits without altering them, I get a non-computable sequence. So it's a very easy task to perform. Okay? So print my source R and print R over bit. So in general, this kind of question, like I have a class of objects and my goal is to get one of them, is what we call in computability theory math problems. It's kind of like the analog of, I guess, search problems in complexity theory. Right? So the question is, given a class of objects, how hard is it to generate a member? And you can even compare two classes. I say this class is easier than this class if whenever you give me a member of this one, I can compute an element of this one. So we can even compare math problems in terms of difficulty. Right? And now for those that cannot be generated deterministically, you can ask whether they can be generated probabilistically. So I'll give you a few important ones, like one of the key math problems in computability theory. So this one we just talked about, the kind of like the simplest non-computable math problem, generating a non-computable sequence. This one also is important, like generating a random sequence. This one is very central. So PA, it's like completions of piano arithmetic. So imagine piano arithmetic, so it's like on the language of arithmetic, and you want to know if you can, so if you can make a coherent completion of, so you write all the possible sentences of arithmetic, and your goal is to put a 0 if you decide that this is false, and a 1 if it's true, as an axiom. You put that as an axiom. And your hope is to get a coherent completion of it. So basically, this is equivalent to generating an infinite sequence. And Gödel's theorem tells you that you cannot do this in a computable way. Right? This is exactly Gödel's incompleteness theorem. There is no computable, complete, coherent extension of piano arithmetic. Right? But there are such completions, they're just not computable. It's a whole class of objects. Right? And I call this math problem PA, generating a completion of piano arithmetic, coherent, preferably. High. So these are the functions that behave a bit like, for people who know what this is, the busy-beaver function, the function that grow faster than any computable function, than any total computable function. It's called the high. If you have the haunting problem, it's enough, but it's not quite necessary. So it's kind of a nice class of objects that we use in computing. H high for hyperimmune. It's the dual of this. I'm not asking that you grow faster than every computable function, but you should not be dominated completely by any computable function. So you have the right to be infinitely often very fast and infinitely often very slow. But this forces you to be infinitely often very fast. Right? This is always very fast, and this is infinitely often very fast. And DNC functions also, again, like the definition may seem a little arcane, but it's like a central concept in computability theory. So you have the list of all partial computable functions, and I want to have a function which differs on the diagonal. Right? So, of course, such a function cannot be equal to any of the phi n, because at point n you differ from phi n. So you kind of like defeat every partial computable function on the diagonal. So none of these things, for obvious reasons, have computable solution. You cannot use computability, deterministic computability to generate a random. This is Gödel's theorem. Of course, if you have a computable function, it cannot dominate all computable functions because it doesn't dominate itself plus 1. Same here, and a DNC function, this ensures that it's not computable. So all of these problems are non-trivial math problems. So the question is then, well, how about, can we do them probabilistically? A non-computable sequence, the answer is yes, I just told you. You just take your random bits, you print them, there you go. You have a non-computable sequence with probability 1. Motion of random, same. Just print your bits, it's random, right? Motion of random, you get with probability 1. PA, no, for the same, I won't give the exact proof, but more or less the same proof as what I gave for the holding problem. You can kind of have a self-referencing sentence. You know, it's like, I'm a liar, blah, blah. You can do that also to try to trick a probabilistic algorithm. But I'll come back to that. So the PA is no. high, it's also low. If you have a probabilistic algorithm which produces a fast-growing function with probability, say 98%, you just wait to see enough values of your algorithm, and then you take the max plus 1. That's computable, and that's going to defeat your probabilistic algorithm on very many values. So another chance. Hyper-review will be very interesting. So this is the next section. So just wait for a few slides. And DNC, yes, that can be done, because remember, I just want a function f which avoids phi n of n for all n. So basically, for a given n, I have to avoid one value. I have no idea what this value is. All I know is I need to avoid it. Well, what I'm going to do is I'm going to take a random value between 0 and something very, very large. I have only a small chance to end up with this bad value, even though I have no idea what it is. If I pick at random between 0 and something large, I will have to be very unlucky to just end up with this particularly bad value that I'm trying to avoid. So DNC is very easy to do actually at random. And in fact, it's related to Kolmogorov complexity, but this is another story. Okay, so we can see that among math problems, among those that are not deterministically feasible, we have some of them that are probabilistically doable, and some of them that are not even probabilistically doable. So, I'm going to come back to this one, because this one actually has a very interesting story. So, when randomness actually helps us. So again, we've seen some examples, but it's a bit disappointing. Because the examples I gave you that could be solved probabilistically, it was not very exciting. It's more like take something random and kind of print it. Right? That's what we did for non-comp. This is what we did for Markov random, and even for DNC. It's like take a big number and just at random and then print that. Right? So not really like, you don't really see the randomized algorithm. Right? But for HI, hyperview, and other problems related to that, such as one genericity, which I don't want to touch in this talk, there is a much more interesting story. So the first person who proved this was Martin, the Martin of Martin determinacy in the 60s, and the argument was refined by Kurtz in the 80s. So HI can be solved probabilistically, and the probabilistic algorithm behind it is less trivial than just pick a random number and print it. And actually, it's really the only type of non-trivial probabilistic algorithm we know in computability theory. And I like to call it fireworks arguments because it was in a paper of Sasha Shen that it was described with this analogy. So let me explain. I'm going to take a step back to explain the analogy, and then we'll come back to the computability interpretation of it. So, fireworks shop. So here's the game. You arrive in a fireworks shop. The fireworks that are sold here are very cheap. So you're like, they're so cheap there, actually some of them may be deficient. But because they're so cheap, you might actually test a few at the shop, or maybe in the backyard of the shop, to not make the shop explode. And then, once you've tested a few, then you will buy one and take it home, untested. Right? So our goal, either you buy one untested and you take it home, and it has to be good, because if you arrive home and then it's bad, then you lose the game. Or a test you conduct in the shop fails, and then you get to sue the owner. It's like an American game. If you get to sue somebody, it's a win, right? So either of these scenario is good for you. The bad scenario is you take home a bad one. So it looks like this. You have your end fireworks. I can test one. I test the second. It doesn't go off, even though I tested it. That's a win. Or I go here. I say, okay, test that one, test that one, test that one. Okay, seems like they're good, so I'll buy this fourth one. And then I go home. If it goes on, I win. If it was bad, then I lose. Okay? So that's the fireworks shop problem. And it's quite clear that there is no deterministic strategy to win this game. because if the shop owner knows in advance what we're going to do deterministically, it's going to know we're going to try this one, and this one. It's going to give us the one that he knows we're going to take home. He's going to put a bad one in this particular position. So if we announce a strategy in advance, the shop owner is going to trick us. But there's a very easy probabilistic strategy. Is you pick a number at random between 1 and n plus 1, you test the first k, and you buy the kth one, unless we've already found a flawed one. So this is a pretty simple algorithm, and it works. It's in fact optimal, actually. So if you have n fireworks. So why does it work? So it works with probability n over n plus 1, so very close to 1. Because the only bad case is we pick the first bad fireworks in the shop. Because if our k lands before the first bad one, then this is the one we take home and it's going to be good. And if our k lands after the first bad one, then the first bad one will get tested in the shop and we win. So the only bad case scenario is the k we pick is just, bad luck, it's the first bad fireworks in the shop. So, it's not a super complicated algorithm, but this is how you avoid, this is how you win with high probability. Okay, so what does this have to do with anything? So, to go back to my problem, I want to generate something which is hyperimmune probabilistically. So I have my list of partial computable functions, and I want to defeat all total ones. I want to not be dominated by any total function. So some of them are partial functions. They're not defined on some values, right? So Turing machines, so they may be undefined. These I don't care about. So suppose you give me a phi I, there are two things. If phi I is partial, I don't even have to worry about it. I can just say, well, this one is already taken care of. It's not going to dominate me, why? Because it's partial. Or, if I know that phi I is total, I take any n, I run phi I on n, and I define my f of n to be phi n plus 1. And then I defeat it. I will not be dominated by phi I. Problem. Given an I do not know in advance if phi I is total or partial. And I have no computable way to tell. So what I will do then, I'm going to use fireworks for this. Right? For each I pick a fresh number between, say, 1 and something very large, and I repeat the following process. I pick a fresh number w, I define my function to be 0, so here I have the hope that phi I is partial. Right? And I just run phi I of w and wait to see if it terminates. So it's like testing the fireworks. And then while I wait, I take care of other phi I. And if this never goes off, then it's okay, I win. Never goes off, it's like a bad fireworks. So this is the winning case with the bad fireworks. And if eventually it terminates, that means the fireworks does go off, then I say, okay, my test was okay, so now I need to pick a new w. And I repeat this ki minus 1 time, which is exactly the number of tests in the fireworks shop. Right? So here, and if finally I arrive at the number that I pre-decided in advance, at the number of tests I was going to conduct, and I say, okay, now I take home, this is the take home, take a final fresh w, I stop all other strategies, and I wait for now this to terminate. So now this is like the take home box, and I wait for that to terminate. And if it does, I do this. And the bad case scenario is just the one I decided to wait on and stop other things. Just this one is going to be partial. That's a bad case scenario, but that's the only bad case scenario. So just like in the fireworks shop, my bad case is when I take this one, which is defined for all the w's picked, and just undefined for my final pick. And as for the fireworks shop, well, I can bound the probability of that happening, right, to any epsilon that I want. So I can make the total probability of failure to be less than, say, 1%, or anything you fix in advance. You can never do exactly 1 probability 1. This can be shown. But you can get as close to 1 as you want. Okay, so that is the fireworks type argument. So supposedly this talk is also a bit about me. So what did I do in this direction? I actually wrote 3 papers. One with my former PhD student, David Paté, where we really extended fireworks arguments not just to like simple cases like priority constructions and forcing construction. Forcing construction is when you build objects by progressive refinements. And we managed to combine Fireworks argument with something called Bushich reinforcing, which was very informative in the study of diagonal non-computable functions. And what's fun about this paper is like we use various layers of fireworks. So you start a fireworks test, and in this fireworks you have a sub-fireworks, so it's kind of an interesting dynamic. I would like to tell more, but we have to keep moving. With Polar, we did something also interesting. We say, okay, fireworks argument, I told you, right? It's a randomized algorithm, so I can ask how much randomness do I need on my random tape. And it turns out margin of randomness, which is a very strong notion of randomness, is not good enough. There are margin of random numbers that if you use them as your random tape, they will not let you succeed at your fireworks argument. You need more. So exactly where it fits was completely unclear, and we found that in fact in the whole zoo of randomness notion, the good one is something called Demuth randomness, which is much stronger than margin of randomness and has many applications. But again, takes a bit of time to define. But it's just we almost precisely nailed where fireworks arguments fit in the hierarchy of randomness in terms of how much randomness is needed to make them work. And finally, also a cute result with Steifer and Delerose when they came to visit the LABRI. We used fireworks technique to solve an old question, which is the question for the problem of probabilistic versus deterministic gamblers. So I told you there are many ways to define randomness. One way to define randomness is to say that there is no probabilistic machine that can make bets on the bits of your sequence and be better than average at predicting. And there was this question is whether, if your guesser has access to probabilistic means, can it do better than deterministic ones? And we used fireworks argument to build a sequence which cannot be guessed by deterministic gamblers, but can be guessed by probabilistic gamblers. And the probabilistic is doing some sort of fireworks to get there. But you still have to juggle, there's a bit more to it than that. You have to look at what is the induced measure by the fireworks construction and build your sequence relative to this measure, so there's a bit more to it. But it definitely uses the fireworks idea in a crucial way. And also forcing. So that's what I did. So now let's take a step in the other direction and consider when randomness does not help. And one thing we looked at is, okay, when randomness is useless, can we quantify the uselessness? So that sounds a bit mystical, but I will explain what it is. So I told you about the math problem PA, completing piano arithmetic. And there is this question whether you can use probabilistic means to get a completion of piano arithmetic. And I told you that it's not too hard to prove that no, it cannot be done. But what is fascinating is Levin proved a quantitative version of this. What he proved, he said, okay, I have a universal Turing machine. So I can also consider the universal Turing machine with a random oracle, a random tape. So that means I have a universal probabilistic algorithm. So if I want to study how well a probabilistic algorithm is, how it works, I can run my universal one, and if the universal one doesn't do very well, then no other probabilistic algorithm is going to do very well. Right? So we can use this universal probabilistic algorithm to gauge how difficult the problem is to solve probabilistically. And what Levin proved is that for well-chosen encoding, the probability that your universal probabilistic algorithm is going to complete piano arithmetic for statements up to length n is 2 to the minus n, so extremely small probability. So even if you care about a very small completion of piano arithmetic, you're trying to decide, I don't know, Goldbach conjecture or very short theorems, and you're trying to get a completion of that, you're going to fail miserably, right? Because this is very exponentially fast growing, exponentially decreasing. And also, what intrigued us is a set of computer P arithmetic is formed what we call an effectively closed set, or Python 1 class, as we call them in computability theory. And if you want to think of them, you can think of them as the set of paths through a computable tree. If I give you a computable binary tree, its set of paths is what we call an effectively closed class. And we felt with Chris that there was really something going on that went beyond just P arithmetic. Like it really had something to do with Python 1 classes. So we extended Levin's theorem to make a definition. We call the Python 1 class deep. If for some computable function h, I can gauge how quickly my probabilistic algorithm fail at producing a path through that tree. But here, let's say we have like a existential. I don't really care what is the h. I just want to have an effective bound on how the failure rate. And we were able to actually find, with this definition, a lot of examples of things that had been studied in the literature. So one example is very fun. It's a Levin shift complex sequences. So they're infinite sequences, such that not just the prefixes, but the all windows, all chunks of them look random. So it's very strange, because if you have something random, you feel like you should have a lot of zeros somewhere. So, but if you allow to not be completely random, but say 1 minus epsilon random, like 99% random everywhere, you have such sequences. And actually, they cannot be generated probabilistically, and even they form a deep class. You can find a bound on how difficult it is to generate them. Unbounded list of incompressible strings, a string of high Kolmogorov complexity. It's easy to get one, but if you want to get many, then this is actually hard to get, and that forms a Python 1 class with proper encoding. Some subclasses of DNC functions, complicated. Levin neutral measures. Again, that's only for people who know what that is, but they're just like a large number of examples from Python 1 classes in the literature actually turned out to be not simply impossible to generate probabilistically, but you can actually compute a bound on how difficult it is to get them at random. And what prompted us to define them in the first place is that there are many theorems in algorithmic randomness that involve P arithmetic. So I'll give you one of them, by Frank Steffen. If I have a Markov random Z, and it computes a computation of P arithmetic, then in fact it computes the halting problem. And of course the halting problem is enough to make a computation of P arithmetic. So it's kind of strange. It's like basically a random cannot really compute PA unless it already computes 0. And there are Markov random wheels that compute the halting problem. For people who know, like Shaggy Omega is an example. Or this one by Day and Miller. If a Markov random Z does not compute a member of PA, then it doesn't compute PA even if I add what is called a K-trivial, so something which is close to computable but not quite. So even if I increase a bit its computational power, it still doesn't compute a member of PA. Or, that was in Levin's original paper, any member of PA has infinite mutual information. That means it knows a lot about the halting problem. It doesn't compute it, but it has a lot of information in common. And so in fact what we proved is that it really, none of this is really related to PA. What really makes it work is the depth, like deep Python classes. So all of the theorems are true if I take a deep Python class instead. But why do we call them deep? It's a very strange name. It's, well, because we're vaguely inspired by an existing notion, which is called logical depth, due to Bennett. So Bennett came up with this notion, what we call depth, to remedy a flaw in the theory of Kolmogorov complexity, which I alluded to at the beginning. Right? We say like basically Kolmogorov complexity equates complex and random. But sometimes in the colloquially, complex means sophisticated. Right? And Kolmogorov complexity doesn't capture that. So I'll just to get like an idea, like a visualization. So you have high complexity objects. Sorry, Mr. Pollock, like something like random scribble, like no order. Very low complexity things, like sorry, Mr. Miro. So just very simple, almost no information. And in the middle, you have things of two types. You have things that have intermediate complexity because I just took some randomness out, and you have things that are called complexity because they're sophisticated. This is what we feel like. Like this one is still randomness, just watered down randomness, artificially watered down randomness, and this is sophisticated, it's deep. Right? And so Bennett was like, okay, what's going on? Like, how do I, still if I want to work with Kolmogorov complexity, how do I formalize this? And Bennett's idea is like, oh, what makes this one deep is like, if you have a description of it, it would still take a very long time to make this thing. Right? Whereas this one, okay, well, you just still do random scribble and then you cut in half. It's still very easy. Right? This one takes a long time to make. And this was his idea. They say, okay, if I have something which is sophisticated, there's going to be a big difference between its Kolmogorov complexity and this Kolmogorov complexity if I put a time bound. This T means I have a time bound T. I only allow programs that work in short time. I mean, if I give you a small T, then the Kolmogorov complexity is going to be much greater than if I give you all the time in the world. And he came up with this definition for infinite sequences. It says infinite sequence is Bennett deep if for every computable bound, this tends to infinity. If I put a bound, the Kolmogorov complexity is high. If I put no bound, well, it's very high, it's low. And it works quite well, at least for some of the simple examples. The halting set is deep. At least we want that. If X is not deep, you cannot turn it into a deep sequence via a quick reduction. And it's a very rich concept. So there's been many papers by Weiders, Laprok, Lutz, Steffen, and Moser. The only difficulty of the theory is we didn't have a lot of good examples. So I guess there were, after the late 90s, there were less papers because we didn't really click well with the with all these natural Paisoan classes that we talked about. And at the time, we were writing the paper saying, okay, it looks a bit similar, like the classes we look at, they have some structure, so it's a bit reminiscent of Bennett depth, but we were interested in other questions, and we just gave that name and forgot about it. And it's quite embarrassing that, in fact, it's extremely related. We discovered that several years afterwards, that the two notions are very closely related. Namely, if I give you a deep Paisoan classes, all its members are in fact deep in the sense of Bennett. So really, it's very, very related. And although we don't quite have a converse, if I give you as a math problem the task of generating a deep Bennett sequence, you cannot do it with a probabilistic algorithm. It doesn't form a Paisoan class. It's not quite a deep Paisoan class, but it's still at least it cannot be done probabilistically. So what does that mean? Two things. First of all, we have a very curious correspondence between sophistication and how hard it is to compute something using random algorithms, right? Because there is clearly a very strong connection between Bennett depth and R depth, right? And seemingly they're two separate things in some sense. Sophistication and difficulty to generate at random, they're not quite the same thing. But in fact, there really is a connection between the two. And plus, because of this theorem, now we have a lot of examples of Bennett deep sequences. Shift complex, bounded DNC, PA, etc., etc. So we living neutral measures. So we introduce a lot of examples of deep sequences, Bennett deep sequences. So that was a contribution to this. Okay, another line of work unrelated to the previous one. What happens when you integrate randomness to logical theories? So there are two lines of study that I looked at in this direction. The first one, suppose I have a logical theory T, like made of axioms. Is it something we can even think about to enrich my theory using random axioms? Like I just add axioms at random in my theory T. Is it even something that is worth thinking about? Another thing is what happens if within my theory I add axioms that say randomness exists, which is not quite the same thing. So these are two different questions, but they're kind of like logically, like you think of them in terms of formal logic. So for the first one, to give an example, suppose you have a theory which is, as usual, just so we can state theorems like Godot theorem. You have a theory T which is powerful enough that you can embed arithmetic, like for example ZFC. Imagine you have a formula with a property. You have a set of integers, and your formula doesn't prove any phi of A for any A in the set, but you know for sure that most X have this property phi in your set A. That you can prove in your theory. Then what would you like to do? you say, well, okay, I know that should be true for almost all R's inside this set A. So I'm gonna pick an R at random or a few, and I can add these things as axioms, right? Because most of them will have property phi, and I can prove this. So I want to add that to my theory, and I get a new theory, which is probably sound, because most of them have property phi. So this was a question on Lipton's famous blog. He was asking, okay, is this a reasonable thing to do, and is it useful? That is, if I fix a particular property psi that maybe is not provable in my theory, do I have a chance that add random axiom and suddenly prove psi? So that's something we looked at with Romashchenko, Shantavno, and Van der Meeren. And we did prove that, yes, it's a reasonable thing to do. If indeed you can prove that most of your x's have such certain property, then you can do that and keep enriching it. And in fact, you can make a nice proof system that way. You can, if you have this like symbol that says you can prove with probability p with this process, and with error probability epsilon, because of course you always have an epsilon probability to become inconsistent. So this is like the probability, like t proves phi with probability p and epsilon probability of error, right? So of course, if you prove phi, you prove it with any error you want. If you always prove something with probability 0, and this is the one that captures what I say, like if most x's in A have property R, and with R you can prove phi, then you can prove phi with like basically the average value. I won't get into the details. So you kind of make a proof system out of this. And this proof system actually is completely reasonable, but once again, de-randomization is possible. So if you can prove something with more probability, like a higher probability than the error probability, then in fact you can de-randomize your proof, and just it was provable in the first place. So once again, it's like the kind of a uselessness of randomness that you can de-randomize your proof. However, you still gain a bit, like unless NP is equal to P space, which I guess we don't believe, then some proofs become shorter that way. So it's useless qualitatively, but quantitatively you still gain a bit. You're going to make some proofs a bit shorter. Okay, now I told you about axioms about randomness. So the setting for this that we use is so-called reverse mathematics. So reverse mathematics is a branch of logic when you try to study classical mathematical theorems under the length of computability theory. And you try to kind of order those theorems in terms of how strong they are, like constructively in some sense. And why can you do this? Is because the many theorems, I guess, you can find in the undergraduate textbooks have this for all x, for every data, there exists some y with this property. So that x and y are second order objects, so something which you can code into an infinite binary sequence. And phi is some property. So let me give examples. That takes us back to our undergraduate years. Right? The Bolzano-Weierstrass theorem. If I have a sequence x of real numbers between 0 and 1, then there exists a converging subsequence y of x. That's a theorem of this type. For all x, there exists a y with the property that you are a subsequence and you converge. Converging is an arithmetic thing. For all rational epsilon, there exists an and blah blah blah. This is converging is an arithmetic statement. Or Bohr's fixed point theorem. For every continuous function, there exists a fixed point. And for all x, this is my x, the fixed point is z. A continuous function can be represented by an infinite binary sequence. Take my word for it. And this one is interesting. Ramsey's theorem. You take all pairs of integers, and for each pair you give them a color red or blue. Then there's the theorem that says if you do that, no matter how you color your pairs, there's going to be an infinite subset R, such that all pairs of elements of R are going to be either all red or all blue. This is the famous Ramsey theorem for pairs. It will come up again. And the big discovery of reverse mathematics is that in fact most theorems fall into one of 5 categories. There's 5 classes of theorems that are equivalent to one another in terms of like difficulty of the constructive level, I would say. But there are many theorems that escape this. And we have a nice zoo of all of these are theorems that have been looked at in reverse mathematics and that are not equivalent to one of the big 5 classes. Right? So we have a whole so-called reverse mathematics zoo. And what we did, so we looked at, again, take a probabilistic view at these things. So for leg, there is a y phi xy. Now, let me say like this, in fact, is a bit reminiscent of the math problems. Like if I give you an x, you can think of the y's as a solution to a problem. Like for example, I give you, Weierstrass, I give you a sequence, find me a subsequence. Right? It's kind of a math problem for it. It's a parameterized math problem. I give you an x, find me a y. So if you think of these as math problems or parameterized math problems, then you should start thinking about them in a probabilistic fashion. And indeed, it's very interesting because there are theorems for which the first answer is no. You cannot do it deterministically, but the second, probabilistically, you can. And there's a nice example, which is the so-called Rainbow-Ramsey theorem. So it's a weak version of the Ramsey theorem for pairs. So now imagine all your pairs are colored this time with infinitely many colors, but each color is used at most twice, or k times for a fixed k. Then there exists an infinite rainbow. There exists an infinite subset of integers such that every color is used at most once in the coloring of this subset. You can prove that there's a computable coloring that has no computable infinite rainbow. So basically that means you cannot computably solve the rainbow problem, but you can do it probabilistically. The big theorem of Cima and Miletti 15 years ago, that if you have a coloring of the pairs, you can probabilistically obtain an infinite rainbow. And in fact, it's related to DLC, but again, this is another story. So randomness can help even in reverse mathematics. And that particular result gives us a separation. Now we know that the rainbow doesn't prove, right? It's like a proof theoretic. You cannot prove the full Ramsey theorem from the Rainbow-Ramsey, because it's possible to show that the Ramsey theorem, randomness does not help you, whereas it helps for the Rainbow-Ramsey. So if I add an axiom, say random things exist, suddenly I can prove the Rainbow-Ramsey theorem, but I cannot prove Ramsey's theorem. So it's like a separation of principles using randomness ideas. And what we did with Pate and Schaefer is we looked at the zoo, and we said, okay, what theorems are probabilistically possible and what those are not. And we actually are almost at the time, the zoo has grown, there's more open questions. At the time, we kind of solved, like for every particular problem in the reverse mathematics zoo, we say, okay, this is probabilistically solvable in green, or it's not probabilistically solvable in red. The interesting proofs are actually the red ones. None of the green ones were very interesting. We didn't have like fun fireworks, or it was always a bit trivial, kind of, or adaptation of existing. So the green ones were a bit boring, but there's some fun stuff happened for the red ones. So this is really where most of the work happened. Okay, so and now I have to rush a bit because we're running a bit late. I have one quick last section on the power of de-randomization. So what is it about? So far in my talk, every time I say, oh, you can de-randomize, it was kind of like, oh, it's a bit sad. That means randomness is useless. If I can do something probabilistically, then I can do it deterministically. It means randomness does not help me. But there are a couple of instances where, in fact, this is a feature that I would like to show that something is computable. I don't know how to do it. Well, all I have to do is to find a probabilistic way to do it and say, well, if there is probabilistic, then there is a deterministic one. And I will give you one example on a paper that I had with Allen and Slayman. And it concerns Diriger's problem. So suppose you're given a bounded open set, I should have said, bounded open set in Rn, and the boundary is, I'm not going to give details, let's say smooth enough. And on the boundary you're given a continuous function, real valued function. Diriger's problem is whether you can find a solution on the whole, like on the whole U plus its boundary, such that on the boundary it's equal to your boundary condition, and inside it satisfies like the Laplacian is 0. It's like a temperature, but like Laplacian 0 is like stable temperature. So you imagine like somebody fixes the temperature on the boundary, and you want to find like a solution, like a stable temperature in the inside of your envelope. So it's a very all problems. So here, see, here is in 2 dimensions. So I have my open set U, this is the boundary. I give you a phi on the boundary, and can you feel inside the temperature in a way that on the boundary, of course, it should coincide with phi, this is the constraint, and inside the Laplacian should be 0. So what we looked at is a constructive version of the classical one. The classical theorem is like, if your boundary is smooth enough, there is always a solution, and it's unique. It's not easy to prove this. It's a lot of work, but it's a lot of name dropping, right? Gauss, Diriger, Riemann, Weierstrass. But we looked at the computable version of this. Now we say, okay, suppose this problem is given to me in a computable fashion, so I have a computable curve, a computable phi. Can I find a computable solution inside? So computable here, like we're dealing with computable or real valued functions, so we mean like computable with arbitrary precision. And well, that's completely obvious. But in the classical theory of the Dirichlet problem, there is a nice probabilistic solution, which goes like this. You want to know what is the value of your function, the unique solution at x. What do? You start a Brownian motion at x. So think of an infinitesimal random walk. You walk in a very disorderly fashion, and then you wait until you hit the boundary. If your thing is bounded, eventually you're gonna touch this boundary. And you compute phi at this point of intersection. And you try that many, many times to get your expectation. It turns out that this expectation is the solution to the Dirichlet problem. Why? Because Laplacian 0 is kind of like an average thing. It means that you're the average of your infinitesimal neighbors. So if you perform a random walk, your expectation should be the average of the infinitesimal expectation. So that's why the Brownian motion will work. Okay, so that actually can be almost effectivized. So you take this x, and you make your random walk, you hit p of x, and then you do that many, many times, and then you compute your expectation. Right? And that's a solution. And well, this is a probabilistic way to do this. And this is almost effective. Almost. That means that if now you give me randomness, I have a u, I can kind of use a computer simulation to make my Brownian motion until I reach a point, except that there is a small problem. It is not quite computable to find the intersection, because we have approximation up to arbitrary precision. And if I know at my Brownian motion, I know that at time t I was here, and at time t plus epsilon, I'm here. I was like, oh well, probably my intersection is somewhere here. But maybe not, because Brownian motion is tricky. Maybe it was doing something like this, and my intersection is in fact very far. And I never know for sure. There is always a very small chance that my Brownian motion did at the last minute went around. So it's not quite computable, but it's almost computable. And there is a theory of this, it's called layer-wise computability, which is due to Warwick and Roth, and in fact it is good enough for the randomization. So because this is layer-wise computable, you prevent very unlikely events from happening, then you can de-randomize. And so we have a computable solution with de-randomization. And there are other theorems that use also this technique, such that an infinite version of Lobach-Local lemma, Bialogniantsev, which also requires layer-wise computability, and has application of reverse mathematics, so it's all coming together. Okay, so it's time to wrap this up. So I hope I've convinced you that there are many beautiful connections between computability and randomness, and maybe some questions for myself, or maybe some of you if you want to think about them in the future. I really insist that we only know really one type of non-trivial probabilistic algorithm, which is fireworks. So really, are there other ones? It really would be interesting to find new, structurally very different type of probabilistic algorithms. So far, we don't have any. I've already showed you that fireworks arguments can be nicely mixed with forcing. Forcing is one of the two big templates for proof. The other is probability constructions. And I do not know a good example of a mixing between probabilistic algorithm and probability construction. So this would actually still be very, especially fireworks, but maybe all these new, potentially new probabilistic algorithms, this would be nice. And I didn't touch about that, it's more like a kind of like a hint at Vasco, because in 2 weeks I will go to a workshop at Viral Degrees, which are kind of in between reverse mathematics and math problems. So can we also look at those under the lens of probabilistic arguments? And maybe this, of course, I'm less competent, but are there maybe applications of what I talked about to complexity theory? Is there some kind of fireworks argument that